My name is Lucas Tabajara from Rice University, and this is a joint work with my advisor Moshe Vardi, on which we take the first steps in bringing the problem of LTLf synthesis under partial observability from the realm of pure theory into practice. The roots of the problem we're trying to solve date back to 1989, when Pnueli and Rosner first introduced the problem of LTL synthesis. In this problem, we are given a specification as a formula in linear temporal logic, or LTL, with its variables partitioned into input and output variables. We then want to automatically synthesize a reactive system that is guaranteed to satisfy this specification. This system interacts continuously with an environment, receiving inputs and emitting outputs, and guarantees that for every sequence of inputs, the sequence of outputs it admits satisfy the specification. LTL synthesis under partial observability, also called LTL synthesis with incomplete information, is a variant of this problem where the set of input variables is further partitioned into observable and unobservable inputs. In this case, the system has to satisfy the specification without ever seeing the values of the unobservable inputs. For example, here we have a specification for a system that receives requests from two processes, represented by the observable inputs R1 and R2, and grants those requests by setting the output variables G1 and G2. However, the specification says that a request should only be granted if it doesn't come from a buggy process, represented by the unobservable inputs B1 and B2. If the system was able to observe the values of B1 and B2, it would be able to always choose the outputs correctly. Since it can't, however, this specification is actually unrealizable under partial observability, even though it would be realizable in the original formulation, which assumes full observability. To clarify the differences between the two variants, here I show a side-by-side comparison. In synthesis under full observability, we are given a specification as an LTL formula phi and a partitioning of its variables into inputs and outputs. We then want to synthesize a system, which we can see as a function from previous assignments of the input variables to the next assignment of the output variables. At every step, the system looks at the past history of inputs and chooses an output, and the resulting input-output pairs must satisfy the specification phi. In partial observability, on the other hand, the system function only has access to the assignments of the observable inputs, but the specification must still be satisfied regardless of the value of the unobservable inputs. Even though LTL synthesis under partial observability has been around for over 20 years now, no tools implementing algorithms for solving this problem exist. It's unlikely that this is due to its theoretical complexity, since it has the same 2x prime complexity as synthesis under full observability, for which many tools have been developed over the years. It's more likely that this is because of algorithms for partial observability being conceptually much harder to implement. A proposed solution has been to focus on LTL over finite traces, or LTLf, which is a variant of LTL that uses the same syntax but interprets formulas over finite rather than infinite traces. Although LTLf synthesis has the same 2x prime complexity, it has simpler algorithms, which has allowed LTLf synthesis tools to emerge that even outperform LTL synthesis tools. The hope is that by combining synthesis under partial observability with synthesis over finite traces, its conceptual complexity will be balanced out, and algorithms will become simple enough to implement in practice. Another motivation for investigating LTLf synthesis under partial observability is that this problem is a generalization of both LTLf synthesis and planning under partial observability, a widely studied problem in AI. A natural example is that of a robot that navigates through an environment performing tasks, but this robot can only sense its local vicinity. The robot's sensors can be modeled by observable inputs, while details of the environment outside the range of the sensors are unobservable. In 2016, Di Giacomo and Vardi proposed two algorithms for LTLf synthesis under partial observability. The first, based on standard techniques used in planning, is called belief-states construction. However, this algorithm adds a third exponential to the complexity, which led them to propose an alternative projection-based approach. By carefully choosing the order of operations, this approach is able to achieve the optimal 2x time complexity. However, this work performs a purely theoretical analysis with no empirical evaluation. And furthermore, since then, no tools have been developed to solve this problem in practice. Therefore, our contribution in this work is to investigate for the first time LTLf synthesis under partial observability in practice. We do this by first implementing both algorithms in a pre-existing state-of-the-art LTLf synthesis framework. We then identify a third algorithm that emerges naturally from using this framework, and finally perform an empirical evaluation comparing the three algorithms. To our knowledge, this is not only the first empirical investigation of LTLf synthesis under partial observability, but of synthesis under partial observability in general. The main questions that we want to answer in our investigation are: does the theoretical analysis accurately predict the performance of these algorithms in practice, and how does the third algorithm perform compared with the other two? The LTLf synthesis framework that we implement these algorithms in is called Syft. The Syft pipeline starts from a specification in LTLf, which is then converted into an equivalent first-order logic formula. This formula is then given to a tool called Mona, which constructs the minimal deterministic finite automaton that accepts exactly the set of traces that satisfy the formula. This DFA is then converted to a BDD-based symbolic representation, which is used to solve a symbolic reachability game in order to synthesize a reactive system. The question now is how to add partial observability to this pipeline. But before I can answer this question, I'll first go through the two algorithms proposed by Giacomo and Vardi. The first, called belief-states construction, first constructs a DFA over the observable inputs, unobservable inputs, and outputs, and then converts this DFA into a so-called belief-states DFA, whose transitions depend only on the observable inputs and outputs. Each state of this DFA is called a belief state and corresponds to the set of possible states of the original DFA that we might be in. For example, if we start at state S0 and observable input R1 is true, we next might be on either state S1 or S2, depending on what the value of the unobservable input B1 is. The belief states DFA accepts if all possible states are accepting in the original automaton. So given an LTLf formula, we can construct an equivalent DFA that is in the worst case doubly exponential on the size of this formula. This DFA can then be converted into the belief states DFA with an additional exponential blowup, which means that the final DFA is in the worst case triple exponential on the size of the specification. The second algorithm, called the projection-based approach, tries to reduce this complexity by first noting that the belief states construction is equivalent to a sequence of simpler operations. We can first complement the DFA, then existentially quantify all unobservable inputs from the transitions, which can turn this DFA into a non-deterministic automaton. We then perform subset construction to determinize this NFA again, and complement the resulting DFA. The DFA that we obtain after performing these four steps is exactly the belief states DFA. Furthermore, it's not hard to see that the resulting DFA is equivalent to the original LTLf formula phi with the unobservable variables universally quantified, which means that the DFA accepts a trace if and only if that trace satisfies the formula for every assignment of the unobservable inputs. The insight behind the projection-based approach is that rather than constructing a DFA only to turn it back into an NFA on step 2, we can instead directly obtain the NFA without ever going through a DFA in the first place. So while in the belief states construction, we first construct a DFA from the formula and then complement it, in the projection-based approach, we first negate the formula and then construct an NFA from it. The advantage is that while a DFA is in the worst case doubly exponential in the size of the formula, we can always construct an NFA that is at most a single exponential on the size of the formula. Since all other steps remain the same, with the only other exponential blowup occurring during determinization in step 4, the projection-based approach is able to save on one exponential. Now we can go back to the question of implementing these algorithms within the Syft framework. Syft solves the synthesis problem using a combination of explicit and symbolic techniques. It starts off with an explicit phase, where it constructs an explicit DFA from the specification, then moves on to a symbolic phase, where it converts this DFA to a symbolic representation and synthesizes the system by solving a symbolic reachability game. So an important question is, can we take advantage of symbolic techniques to implement these algorithms? It turns out that there is a very natural way to do this, since, as I mentioned before, both algorithms rely on subset construction, either to construct the belief states DFA or to determinize the NFA. Subset construction turns out to be very natural to implement symbolically. To do this, we create a Boolean state variable for each state of the original automaton, so that an assignment to these state variables implicitly represents the subset of variables that are assigned to true by this assignment. It is then simple to construct a binary decision diagram, or BDD, that represents the transition relation of the DFA symbolically. This BDD can be seen as a circuit that computes the successor states based on the current states and the observable inputs and outputs. For example, if we start at state S0, then state variable S0 is assigned to true. Then, if observable input R1 is also true, in the next step, both S1 and S2 will be assigned to true, representing that we have moved to the subset S1, S2. In the next step after that, since S1 and S2 are true, if G1 is also true, state variables S3 and S4 will be assigned to true. The advantage of implementing subset construction symbolically is that symbolic DFAs can be exponentially more compacted than their explicit representation. Therefore, by avoiding going through the explicit representation of the final DFA and going directly to the symbolic representation instead, we might save an exponential in practice. This approach also fits naturally into the Syft framework, since after obtaining the symbolic DFA, we can simply apply the standard symbolic reachability game algorithm already implemented in Syft. There is only one caveat in the projection-based approach, which is that Mona normally only supports constructing DFAs and not NFAs. Therefore, we need to use special techniques based on reversing the formula to use Mona for NFA construction. And more details can be found in the paper. As I mentioned at the beginning of this talk, there is a third algorithm for partial observability that emerges naturally from the Syft framework. We call this algorithm the MSO approach. Recall that the belief states and projection-based algorithms try to construct a DFA for the formula phi with all unobservable inputs universally quantified. The insight of the MSO approach comes from the fact that Mona does not only take first-order formulas as input, but more generally formulas in monadic second-order logic, which can be thought of as first-order logic with quantification over propositions. This means that we can construct an MSO formula with the unobservable inputs already quantified, and give this formula to Mona to construct the final DFA directly. The pros of this approach are that Mona always constructs a minimized DFA, unlike the other two algorithms. This means that the DFA state space is as small as possible, which improves the performance of the rest of the pipeline. The cons are that this DFA is not constructed directly in symbolic form, making the construction more expensive and more likely to run out of memory. To see how the MSO approach compares with the other two, as well as how well the theoretical analysis translates to practical performance, we performed an experimental evaluation using benchmark families based on games with incomplete information. In these benchmarks, we are essentially trying to synthesize a winning strategy for these games. A more detailed formalization of each family of benchmarks can be found in the paper. We evaluated the performance of the three algorithms on each of the two phases. As a reminder, the explicit phase constructs an explicit automaton using Mona, either a DFA or NFA for the unquantified formula in the first two algorithms, or a DFA for the quantified formula in the MSO approach. In the symbolic phase, we convert this automaton into a symbolic representation and solve the game. For the first two algorithms, we use a symbolic subset construction, while in the MSO approach, since the unobservable variables are already quantified, we can use an encoding of the state space in a logarithmic number of state variables. I'll show results for the coin game benchmark family as an example, but essentially the same conclusions were obtained from the other two families as well. Starting with the explicit phase, in this first plot, we show the construction time of the explicit automaton as the size of the formula grows with a parameter n. The first thing we notice is that the quantified DFA is much more expensive to construct. But interestingly, when looking at the other two cases, the cost of constructing the DFA is not much larger than constructing the NFA, even though according to the theoretical analysis, there should be an exponential gap between the two. In fact, when we look at the size of the automata, the NFA is actually slightly larger than the DFA by a constant factor. Although this is going to depend on the specific formula, in all of our benchmarks, the NFA and DFA ended up being of similar size. This shows that we cannot rely on the exponential gap that occurs in the worst case between NFAs and DFAs, necessarily manifesting in practice. In fact, all three automata grow exponentially for this family of formulas, although the quantified DFA has a higher constant in the exponent. This plot now shows the running time of the three algorithms in the symbolic phase, in log scale. Note that the MSO approach scales better than the other two, probably because of the smaller state space of the DFA. In fact, even though the quantified DFA could not be constructed for n larger than 6, in the symbolic phase, the other two approaches timed out even before that. It's even more interesting to note that the belief-states construction actually scaled better than the projection-based approach, even though it has an exponentially larger worst-case complexity. This seemed to happen mainly due to the NFA producing a less efficient symbolic representation. In conclusion, in this work, we presented the first investigation of LTLf synthesis under partial observability in practice, by presenting a symbolic implementation of the belief states and projection-based algorithms, as well as a new MSO algorithm taking advantage of the Mona tool, and then performing an empirical evaluation of these three algorithms. Our evaluation revealed the trade-off between the explicit and symbolic phases, where the MSO approach required a more expensive construction in the explicit phase, but compensated for this by scaling better in the symbolic phase. Overall, the end-to-end running time of the MSO approach was smaller for some benchmarks and slightly larger for others, suggesting that this might be a good approach as long as the quantified DFA is small enough to be constructed explicitly. More surprisingly, the expected exponential gap between the belief states and projection-based algorithms was not observed in practice. Therefore, the main takeaway from this work is the importance of complementing theoretical analysis with empirical evaluation, as integrating partial observability into an existing toolchain and applying it to concrete benchmarks affected the results in a way that could not be predicted by the worst-case theoretical analysis.